Hi and welcome. In the previous lecture, we talked about motion, which is described by Newton's laws of motion, and in particular, Newton's second law is a differential equation that governs these motions. We introduced the concept of a frame of reference, with respect to which position makes sense. So we can define the position of an object, r, which is a vector, and likewise, we define its velocity and acceleration. So the velocity is the first derivative, the acceleration is the second derivative. And then we recall that we defined Newton's second law of motion, which is F is equal to m times acceleration, force is equal to mass times acceleration, which holds so long as the mass is constant and the frame of reference is an inertial one. Now, what is a rotation? A rotation is defined like that. So what is it for an object to rotate? Take this object. It's a pen. We have attached a frame of reference on the object. We call it x prime, y prime. We call this the local frame of reference because it's local. It is called body fixed because it is affixed to the body we're studying. And now take this global frame of reference, the frame of reference of the whiteboard. For this object to rotate with respect to the global frame of reference means for its local frame of reference to rotate with respect to the global one. So say that x prime, y prime is the frame of reference of the pen, then the angle of rotation theta is defined as this angle over here. We will be using the convention that counterclockwise rotations are positive rotations. So this is a positive angle. And a negative angle looks like that. This is a negative one. This is a positive one. Now it makes sense to say that the counterpart of position, it is the angle for rotations, the angle of rotation theta. Then, that said, the counterpart of velocity, that is the derivative of the position, is what we call the angular velocity, which again, according to this convention, is positive if the object spins counterclockwise and it is negative otherwise. And similarly, we can define what is called the angular acceleration, which of course is the second derivative of the angle. Now we introduced another two very important concepts in physics. One was the force and the other one was the mass, which is the magnitude of inertia of an object, how much the object resists to changes in its velocity. And so we have the force, F, and the mass, m. The question we will address and answer in this lecture is what is the counterpart of force, what is the counterpart of mass, so how exactly do we describe a rotational force and a rotational mass, what is it that makes an object change its rotational velocity, its angular velocity, and how much does an object resist to those changes. So what is the angular, so to speak, rotational inertia of an object? To try to answer that question, let's think of the following. How exactly do you open a door? A door needs to rotate to open. Okay, so it has a zero initial velocity. It needs to have some positive or negative velocity, angular velocity, so that it rotates. So take a door. How do you make it rotate? One might say that by applying a force, of course, to the door. Yes, but what if you apply the force over here? Then the door will not rotate. The effect of this force on the rotation of the door will be zero. Let's define that effect by m. Then m, in that case, for this force will be zero. But you will say, no, we have to apply the force somewhere that is reasonable For example, here, in which case apparently the effect will be a positive one. Positive in the sense that it tends to rotate the door counterclockwise, and counterclockwise rotations are positive according to this convention. And then a force like that will have a negative effect, but a non-zero effect in any case. So what is that effect actually of the force? We can define it to be the force times the distance from the point of rotation, with the right plus or minus sign, of course. So the effect here is F times D, and the effect here M is minus Ft, and the effect here is 0. Just to be clear about what we mean by distance of the force from the point of rotation, we mean the following. If you have a door and you apply a force like that, F, and the angle at which you apply it is an angle phi, then the distance is the distance between this point O and the force like that. So you make a right triangle, and this is the correct force, the correct distance D. If this length is equal to L, you can see here from the right triangle, L is the hypotenuse, you can see that D is equal to L times the sine of phi. So the torque is F times D, so F times L times sine of phi. And therefore, if you have, at the extreme case where you apply the force like that, so at this point, but alongside the door, then you can figure out that the torque is equal to 0. And it makes sense because this force will not make the door rotate. As we do with forces, we can add them up and find the total force. Similarly with torques, we can find the total torque. So if you have a door and you push it like that at a distance d1 from the hinge with a force F1, and you apply another force F2 at a distance d2, then the total torque is M total equals F1 d1 minus F2 d2. This is the total torque. Now let's talk a little about, let's write here first of all that the counterpart of force is the torque denoted by an M. We still haven't figured out what is the counterpart of mass for rotations, but we will do so very shortly. Just take the following very simple example. Take a very small object here of mass M, connect it to a rod of no mass, and use this point as the pivot point, as the reference point. Say that the distance between O and M is equal to R. Then this object cannot move either to the right or to the left. It can only move on a circle. Apply a force to the object. Apply a force like that, F. And simply, as it rotates, keep this force perpendicular to the radius. Then you will be applying a torque M, which is simply equal to the force F times the distance R, which is the radius. By Newton's second law of motion, let's see what we have here. We have been describing the dynamics of objects using Newton's second law of motion. So these are all the tools we have. Let us apply Newton's second law of motion. Let's keep this equation 1, and say now that F is mass times acceleration. Let us denote the acceleration simply by A in this case. But if you want to study rotations, the force is not enough. The force doesn't tell us the whole story about rotation. We need the torque. Let us multiply, therefore, now both sides of this equation with R, because if we do so, the torque will appear. So this is the new equation. Torque equals mass times the radius times the acceleration. Is this the equation number 2? Is this the equation we are looking for? Well, it is close, but not exactly, because we have the acceleration here, whereas we are looking for the angular acceleration. Now, what is the relationship? Is there a relationship between the angular acceleration and the acceleration? For that, we have to take this result, we have to use this result from geometry. Take a slice of pizza like that. A pizza of radius r and angle theta. Then the length of the pizza's crust S is equal to r times theta. Now, if you differentiate both sides, you will have derivative of S is r times derivative of theta. So angular velocity is r times velocity is equal to r times angular velocity. And if you differentiate once again, you will have that acceleration S double dot, what we have denoted here by A, is equal to r times angular acceleration. So let us replace here that equation over there, equation number 3. We have now, and this is the equation we are looking for. On the left hand side we have the torque, which is the counterpart of the force. On the right hand side we have the angular acceleration, which is the rotational counterpart of acceleration. And here we have this term mr squared. This must be the term we're looking for. This must be the counterpart of mass, right? Because we have the formula, we have Newton's second law of motion. Force is equal to mass times acceleration. It must be, therefore, torque equals to something times angular acceleration. Well, this something has a name. It is called the moment of inertia. And it is denoted by an I uppercase. In this case, in this example, the moment of inertia is mr squared. And you can see here a very simple observation. The moment of inertia depends both on the mass and the distance from the pivot point. So it depends both on the object and where we are rotating, with respect to what point we are rotating that object. So in summary, so far, we have this very useful table, and we also have the definition of torque. We have Newton's second law of motion, and we also have this equation that the torque is equal to moment of inertia times angular acceleration. And we know how to find the total torque if we have multiple torques exerted on an object. What about the total moment of inertia? If you have an example as simple as that, you have multiple point masses and they are connected on a rod, and this is your point of rotation, and let's say that your masses are m1, m2, m3, and they are at distances r1, r2, r3, then the total moment of inertia is equal to m1 r1 squared plus m2 r2 squared, and so on and so forth. If you have different objects which are not a collection of point masses, point particles, then there are different ways in which we can compute the moment of inertia. There is a systematic way to compute it, but I will just give you a few examples here that are commonly used in practice and in exercises. So if you have a rod of length L and mass m, and the point of rotation is at the end of it, then the moment of inertia I is 1/3 ml squared. A few more examples. So if the rotation point, if the pivot point is at the end, it is 1/3 ml squared. If it is in the middle, then it is 1/12 ml square. This might make a little sense to you. If you have a rod and you try to rotate it from the very end of it, like that, then it rotates more difficultly because the moment of inertia is higher with respect to rotating it from the middle. Like take an object like, I don't know, a ladle or a spoon and try to rotate it from the end, from the tip, and then try to rotate it from the middle. It rotates much easier from the middle. Then if you have a solid disk, then the moment of inertia I is 1/2 mr squared. And if you have a solid ball, then the moment of inertia is 2/5 mr squared. But these are just examples which you don't need to memorize or learn by heart. It is just to demonstrate that the moment of inertia depends on the mass and the size and shape of an object. And it is very important with respect to what point we take the moment of inertia. Let us now give a couple of examples. We have our theory, we have Newton's second law of motion, we have this new equation, and we have the definition of a torque. Let's take this example. You have a small object here attached to a string of length L, and the only force applied to it is its weight. What we are trying to do here is to describe the equation of motion, the equation that governs the motion of this object. We're looking for a differential equation, as we have been doing so far. So this is the weight, but forces are no good for studying rotations. We need torques. So we will, to that end, we will decompose the force mg into two forces. Note here, at this point, that this angle is theta. Therefore, this angle is theta as well. And this force touches theta. Therefore, it is mg cosine theta. Whereas this force is mg sine of angle theta. Now this force is cancelled out by a reaction. This is an action and this is a reaction n, and their sum is equal to 0. It is easy to figure this out because the object doesn't move along this line. It will not move towards the ceiling, it will not move away from that. It just moves on an arc. Now this force causes a torque, and the corresponding torque, M uppercase, is equal to the force times the length L. This one is perpendicular here. In particular, note here that according to that convention, this torque must have a minus sign because it tends to rotate the object clockwise, not counterclockwise. So it is a rotation with a minus sign according to this convention. Then the torque by the rotational counterpart of Newton's second law of motion is equal to the moment of inertia of this object with respect to this point of rotation times theta double dot. And if you recall, the moment of inertia of a single mass at a length L from a point of rotation is m times the distance squared forgot the minus. There is a minus here, equivalently, and we will divide by m, we will divide by L, and the equation of motion becomes L theta double dot is equal to minus g sine theta. That's it. This is the equation of motion. And we can observe here, as in examples such as the free fall example we gave previously, that the mass doesn't play a role. So the pendulum will perform a motion, whatever that is. Actually, it is an non-attenuated, non-dissipated oscillation. We observe here that this doesn't depend on the mass of the object. So, for example, the frequency of this oscillation, or the period of this oscillation, is independent of the mass. All we need to know about this system is described by this very simple equation. So our job is done here. Another example, example number 2. Take now a rod of mass m. The mass of the rod now is uniformly distributed along its length. We recall that when you have a rod which performs a rotation around its endpoint, then its moment of inertia is equal to 1/3 ml squared. Great. What are the forces now that are applied on this object? First of all, this is angle theta again, and this is the center of mass of the object. At the center of mass, we apply the weight. And then again, as we did before, we will decompose the weight into two forces. In particular, this one and this one. This force is cancelled out by a reaction from the rod itself, and this force causes a torque. And since it tends to rotate the object clockwise, the torque is minus mg sine theta times L divided by 2, L half, because the center of mass, it's at the center of the object. So it is force times distance. And now this is equal to, this is the torque, but the torque is equal to the moment of inertia times theta double dot. I will leave it to you to substitute I inside here and write out the differential equation that governs this motion. Let us give one more example. This will be an interesting one. So you have an inclined plane of a constant angle phi, and you have a solid ball over here of radius r. And recall that the moment of inertia of the solid ball is... What are the forces that are applied on the ball? First of all, we have the weight, mg. Then we can decompose the weight into two forces, this one and this one. This one is mg times sine of angle phi, because this is angle phi here, and this is mg times cosine of angle phi. Any other forces? Well, of course, there is, this is the action and this is the reaction. Let us call it N, which makes the ball stay on the plane, because this N minus mg cosine phi is equal to 0. I forgot to mention, before we proceed, we need to specify our frame of reference. So it will be this one. This is the axis y, this is axis x. Okay. And for convenience, let us use this convention. Also to see how it is to use a different convention. So I will take this away from here, and I will bring in this convention. Very good. So what other forces are applied here? I must tell you that this ball doesn't slip. It only rolls down the inclined plane. Therefore, there is a force that keeps it from slipping, and that force is friction, T. The friction between the ball and the inclined plane. So now let us write down the equations. We have equations of motion. Let's write the forces along the x-axis. So it is mg sine phi minus t. And this is equal, by Newton's second law of motion, this is equal to m times x double dot. So this is one equation. Let's focus here for a second. What is T? T is this force which makes the ball rotate because it generates a torque. The corresponding torque, M, is T times R, where R is the radius of the ball. And it is a positive one because we are now using this convention. And we know that this is equal to I times theta double dot. So we can solve for t over here and plug it in this equation. Let me write it out. So this is the equation of motion, but we must notice here that we have theta double dot and we have x double dot. However, these are linked with one another. So recall from the pizza slice theorem that when this is s and this is theta and this is r, we have that s is theta r. From here, we can figure out that, you can't see it there, excuse me. The acceleration is equal to the angular acceleration times the radius. So we can write here that x dot is equal to, I'll write it again. There's not much space on the whiteboard. I will erase this part. So I'm continuing from equation number 3, which is so here we are, theta double dot, theta double dot. I will move all theta double dots on the right hand side. I will now substitute I with this value, 2/5 mr squared. And after doing some math, we end up with this equation of motion, which is, it involves g, it involves r, but it doesn't involve the mass of the object. So again, so long as this object doesn't slip, so long as there is adequate friction between the object and the inclined plane, then this equation describes all that we need to know about the object. So this much about rotation. Next video will be about an example involving all these equations, so as to recapitulate and combine what we know about Newton's second law of motion and what we learned today about rotation. It will be the inverted pendulum. So until next time, thank you very much for watching and goodbye.